Nature is beautiful, isn't it? Just imagine we are composed out of billions and billions of small, inanimate molecules, all of them interacting in perfect harmony and being powered by the laws of thermodynamics. When these molecules are isolated and examined individually, they conform to the all physical and chemical laws that describe the behavior of inanimate matter, right? But then again, here we are. 7 billion of us and counting, all of us of different height, weight, eye, skin, and hair color. Nature is beautiful. But now imagine this. What if we could shake off nature's boundaries, harness the power of biology, transfigure cells from one type to another, print tissues, print organs, map the vastness of our brains, read and rewrite the information of our genomes, or even eradicate inborn genetic diseases? It does sound like something that came out of Star Wars, doesn't it? But trust me on this, the science of the future is today. So let me take your hand and walk with you through the story of molecular biology, where we have been, where we are, and where we're going. Not long after the nucleic acids were discovered in the early 1900s, a bunch of scientists were figuring out what these molecules actually do. In the years to come, and with a lot of controversies, the structure of the DNA molecule as well as the flow of the genetic information was discovered. We now knew how our proteins looked like and what they did. We now knew how our DNA and genes behaved, what enzymes were for, how we metabolized food, and how our cells thrived and survived. We began drafting a blueprint of our organisms, standing on each other's shoulders and delineating those fundamental mechanisms that make us all tick. But one of the basic questions that have always bothered us is how a single fertilized egg cell can give rise to this. With more than 37 trillion cells in our body and more than 250 different cell types, we are the ultimate machines of nature. Therefore, in the 1990s, simultaneously to the process of cracking down our genomes, biologists tried to figure out what constitutes the biological memory of a cell, or that is, what makes a neuron be a neuron. Working heavily, researchers stumbled upon the concept of epigenetics. Epigenetics refers to a number of biological mechanisms which are to be blamed why every cell knows its purpose, identity, and function in our organism, thus enabling a skin cell to remain a skin cell even after it divides, right? But the question is, by knowing the fundamental molecular mechanisms which take part in cellular programming, can we make use of them and reprogram cells' inborn, hardwired developmental pathways and transfigure cells at our desire? One of the first steps towards this effort was already made in 2010 by a group of Stanford scientists who directly reprogrammed adult mouse skin cells into fully functioning neurons with all the right proteins, transmitters, and everything, which was later continued by an experiment which reprogrammed connective tissue cells into fully functioning heart muscle cells. These heart muscle cells, after they have been transplanted into an adult mouse heart, kept on beating together with the rest of the heart, giving hope to heart attack patients of the future. Nowadays, scientists have even been able to perform these reprogramming experiments using small molecules of the size of an aspirin, yielding a brave new world of applied bioengineering, shedding light onto various fields of human disease, aging, tissue regeneration, and development. But it doesn't end there. Tissue and organ manufacturing has been blooming ever since we learned how cells gain their identity. This year, scientists have even been able to produce first mini brains and mini kidneys in a petri dish. illuminating molecular mechanisms behind diseases such as polycystic kidney disease or autism or schizophrenia. On top of that, the first 3D bioprinting methods have already been used to print organs, patient-specific organs, and some hollow structures such as skin, bladder, or veins have already been printed out in labs worldwide, leading to a future where transplants would no longer be necessary. We have always wanted to sequence the entire human genome, to decompile that basic algorithm of life. Therefore, in the 1980s, a big international enterprise to sequence the complete information held in our cells was initiated, and 20 years later, at around $4 billion in cost, the results were outstanding. They complemented our knowledge about how cells function, yielding new concepts of genetic individuality, gene structure, and the flow of the genetic information. These results were so provocative and so exciting, they boosted the development of novel, next-generation sequencing technologies. And today, we are capable of performing the same thing, to sequence an individual's genome in a matter of hours, and for even under $1,000. The prices of sequencing have fallen 100 million times in the last 10 years, which has produced the world's capacity of sequencing human genomes in hundreds of thousands every year, and have been foreseen to quadruple in the years to come. But what does this mean? What does this mean for all of us, for the medicine of today, for the common man? Well, it means that the prospect of personalized medicine is already here today. So let me introduce to you Nicholas Walker, a 6-year-old like any other, admitted to the hospital with a very, very dangerous and serious intestinal inflammation. This caused him to have hundreds and hundreds of surgeries as a child, including the ones where he had a large portion of his GI tract removed. His age and the severity of the condition implicated an immune disorder, but doctors couldn't reach a definite diagnosis for years, thus limiting his clinical treatment. He has lived his entire childhood in great pain, with no hope of a better tomorrow, and with a great certainty that he was dying. The doctors and his family, not knowing where to turn next, did something quite daring and sequenced the complete protein coding region of his genome. They discovered a point mutation in one of the genes which regulates programmed cell death, thus enabling an uncontrollable immune reaction in his belly. By knowing the cause of the illness, doctors performed a bone marrow transplant, and 42 days after the transplant, the boy, Nicholas, was able to eat and drink normally. And ever since, there has been no recurrence of the disease for which he had been originally admitted. Today, he eats beefsteaks and runs around quite happily. DNA sequencing most likely saved his life. Just imagine that. The examples to this date are numerous. With the prices of sequencing falling at that rate, all of us in this room might have the chance to extend our lifespan or quality of life thanks to this. Pregnant women can use this technology to detect genetic diseases of their babies before even the babies are born by just sampling their own blood. Doctors can diagnose rare diseases and tailor therapies towards every individual. Whereas this technology can also be used for saving endangered species, fighting off deadly viruses, or even making the best bottle of Pinot Gris ever. We are in the midst of a genomics revolution, and the world is changing quite fast. And as we're moving towards the end of this talk, I have the immense pleasure to present to you another technique which set the scientific world on fire in the last couple of years. By researching the way how bacteria fight off deadly viruses and foreign DNA molecules, a group of researchers from USA discovered something called the CRISPR-Cas9 system. This CRISPR system was later developed into a very, very potent genetic engineering technique. This technique enables us to precisely manipulate the genetic material of our cells, to deliver, delete, or change the sequence of our DNA molecules with remarkable precision. In the last couple of years, it has been used on human cells, flies, worms, dogs, rabbits, mice, whereas the first genetically engineered monkeys have been born a couple of months ago. This genetic microsurgery has offered us a way to understand the functions of our genes, to see how cells migrate, breathe, or replicate on a molecular level, and to even cure genetic diseases such as sickle cell anemia, cystic fibrosis, or muscular dystrophies. Only in the last 2 years, scientists have successfully used CRISPR to combat hepatitis C virus in live liver cells. They have successfully repaired mutations which lead to blood disorders, and they have even deleted an HIV virus from infected human cells. On top of that, this year, a couple of months ago, in an unprecedented event, a team of Chinese scientists has even, for the first time in the history of our civilization, engineered a human embryo. Just imagine that. We have the power in our hands to change the DNA sequence of any living being in any way we want to, and quite simply, if I might add. Such history-making advances can be as important to this century as vaccines or electron was for the last. Genome engineering will transform everyday aspects of our lives, beginning from basic research, biotechnology, therapeutical advances, to chemical engineering or even energy production. The only limitation is our imagination. There is even a guy who is selling homemade, do-it-your-own CRISPR sets with which you could engineer live cells at your home. But do we know where we're going with this? Do we know enough about human genetics, or animal genetics for that matter, to go through with this? Is this a sign of a bright new future without genetic diseases, or a slippery slope towards unethical uses of these techniques? All of the perspectives we have spoken about today now raise a lot of questions and a lot of concerns. Will the data of genomics be used for treating rare illnesses or seeing if you're compatible with your wife-to-be? You want to be insured? You want to become a pilot, a president? Yeah, sure. Let's just sequence your genome first. Would you really like to have your baby born with cancer predisposing alleles? And can we engineer babies whose genomes we do not like? Will this be a world where rich people can buy new organs and engineer their babies to be healthy and prosperous, whereas the poor ones can't? Will human germline engineering start us down a path towards genetic enhancements? And who will set that arbitrary line between genetic enhancements, aesthetics, and therapy? Human genome engineering has become such a flourishing research concept that several research centers in China, USA, and UK are already working on it, even commercially. You can design a baby of your own. Are we on the verge of genoism, the unethical genetic discrimination of future? But why am I telling you all of this? We are already made in the future. In the last 100 years, we have been living in the world of supercomputers, quantum physics, molecular biology, genomics, deep universe exploration. A second renaissance, if you will. Scientific breakthroughs must be accompanied by changes in scientific communication, legislative boundaries, and public awareness. These base pairs here do not in any way represent the quality of our social and private lives, nor the stability of our civilization. Okay? Not any scientific technique or breakthrough is intrinsically good or bad. And it's really in our hands, in your hands, to wield them properly for the sake of our progress or not. The future is not a place you go to, it's a place you create. So wake up, tune in, think profoundly about the questions and perspectives at hand here, since you, all of you, will be the ones calling the shots of tomorrow. Thank you very much.